And so, as I said, the talk will kind of use this relative Floer theoretic invariants, or some people call them local Floer theoretic invariants or localized Floer theoretic invariants. And usually I talked about the closed string case of this, where you do Hamiltonian Floer homology. And this time I want to do Lagrangian Floer theory, which is, of course, very similar. So I wanted to just recall what that is. So we start with a symplectic manifold, and this is just recalling the invariant. And inside it, we take a Lagrangian, and let's say this Lagrangian is a spherical. And it works under more general. The more general you want it to work, the more you have to kind of develop theory. But for today, it will be enough to just work in this very simple case. And if M is not compact, then we also need to assume some stuff at infinity. M and L are not compact, and we have to assume some tameness at infinity. I'm not going to worry too much about it. And under these assumptions, for any compact subset of this symplectic manifold, I can define this HF, so HF for Lagrangian Floer homology. I will also put this sub M to denote that it's this relative kind of invariant, and it's computed at K using this Lagrangian L. Okay, so HFM KL, and this is not always commutative, but it will be commutative in the example I'm going to work with today. It's not necessarily commutative in general. Associative algebra over the Novikov ring. So the Novikov ring is a formal power series with T a formal variable, where these alpha i's are non-negative real numbers, and these ai's belong to some commutative ring K. And it should be so that the exponents go to infinity as I goes to infinity. Probably everyone's familiar with this. So the construction of this HF, this relative Lagrangian Floer homology, goes roughly as follows. You choose some set of Hamiltonians, some sequence of Hamiltonians, which are growing. And this is what's generally called the acceleration data. And these Hamiltonians are supposed to be approximating the function that's 0 inside the compact subset and infinity outside the compact subset. So they grow, and inside they grow to 0, whereas outside they grow to infinity. And if you're again in the non-compact case, you have to work with admissible Hamiltonians, which allow you to get some C0 bounds. And once you make this choice, you get this diagram of chain complexes over the Novikov ring. These are generated by one chord of L. So you look at the flow of each HI, and you look at the chords which start on L and end on L, but in time 1. So it's freely generated by such chords. And there are continuation maps. There's a differential. So it's exactly like Hamiltonian Floer homology, but instead of doing one periodic orbits, we do chords. And the solutions are, again, weighted by the topological energy of solutions of the Floer equation. Okay, so you end up with this diagram of chain complexes, and then you define the invariant as follows. You take a direct limit of this diagram. That's another chain complex. You complete it t-adically. So you allow infinite sums as long as their coefficients have valuations going to infinity. And you do this thing that I call the regularization. I will not say what this is, but I will just show what it does in an example. And then you take the homology of this complex. And this is, as I described it, it's just a graded module over the Novikov ring, but you can also naturally equip it with a product structure, an algebra structure. by counting pair of pens, the open string version of pair of pens. Okay. So this is the invariant. So let's talk about it in an example. So I will consider the cylinder. So R mod Z cross R with this dp/dq symplectic form, where the coordinate here is P and the coordinate here is Q. And I will consider the Lagrangian, which is this line obtained by fixing the P coordinate to be 0. And I will consider this finite cylinder K inside the infinite cylinder, which is my ambient symplectic manifold. And here I have to fix a grading datum, some trivialization of just the square of the canonical bundle. I will not mention this. There is some particular grading datum that you have to fix to get the results that I'm saying. And if you now compute this relative symplectic cohomology of this Lagrangian, localized at K if you want, or if you want to look at it from the perspective of K relative to N. Okay, the result is as follows. So you look at this this algebra, this explicit algebra over the canonical ring generated by two variables X and Y. And they're subject to the relation xy equals t to the b minus a. Maybe it's better to write it like this. So you modify this ideal. And then you complete this algebra t-adically. Okay. So now what is the idea of this computation? So we want to compute, so we have to choose this acceleration data. And I would like to choose my acceleration data, so which is going to be HIPQ, which, you know, a priori can depend on P and Q variables, to just depend on the Q variable. So just the, if you think about the map that projects to Q, to the real line, so there is a fibration, circle fibration, and I want to fix a function that only depends on the base coordinate. Okay, so this is HI. Okay, and now drawing the graphs of these little HIs, they are of course negative on this interval, which is the image of this, the finite cylinder that I fixed, and they grow as you go, kind of as you leave the boundary of this interval, and they do so in such a way that they're strictly convex. So this they're strictly convex, but until they become linear in these regions. They're just linear in Q variable in these regions, and until that, so it's convex everywhere and strictly convex until it becomes linear. Okay, and this the slope of linearity is supposed to be an irrational number. Okay, so now I'm going to use acceleration data like this. And now you can easily compute the Hamiltonian vector field of such a function. It's just equal to the derivative of little hi evaluated at whatever point I'm at, and you only move in the fiber direction. Okay, so it's hi prime cube times the constant vector field in the fiber direction given to you by the coordinates that we're using. Okay, so now if you look at one quartz, so it's stuff that starts here and goes around and comes back, well, I know it has to lie in the same fiber, so the only thing that it can do is to do this. And for that to happen, you're always going with the same, you're always traversing the same amount of P, and you're supposed to traverse exactly one. So one quartz, you can see, correspond exactly to the point where this derivative is integral. It's an integer. Otherwise, you go around and don't come back to L. So you don't become a one quartz. So all the generators are happening at the point on above the point on this Q line where the derivative is an integer. So there's, for example, one here where the derivative is 0, one here maybe where derivative is 1, derivative is 2, maybe it's 3 here, and so on. Okay, and as I go to you know, as I increase my functions, as I make them kind of steeper and steeper, so approximate infinity, I capture more and more orbits, more and more chords. Sorry. So now, each of these this Lagrangian Floer homology complexes generated by one chords will look like this, where I will always have kind of this derivative being equal to 0, which I will call 1. And then I will have some chords that are happening near here and that are happening near here. So the ones that are happening near here, I will call x. So there's going to be two indices here. So I is telling you which Hamiltonian you're using in this family, in the sequence of Hamiltonians, and n is telling you how many times you're wrapping around. Okay, so there is some xi1, xi2, xi3, up to whatever irrational slope that I fixed for this function, xin. And the same with y's here. Okay, so now looking back at the definition, this tells you what these are. Okay, what these chain complexes are. Now, because of this particular choice of grading datum that I made, all of these generators are supported in degree 0. Okay, so therefore there's no room for a differential, for example. Well, this is just all of these chain complexes are actually just the, modules living in degree 0. Okay, and as I said, there is this kind of extra grading by extra grading on these modules by the winding number. So this winding number is the relative first homology m comma l, and this is equal to z. And the point of mentioning it this way, the point of seeing the winding number as an element here, is to make it clear that if you're looking at a Floer solution where you have one orbit here, one chord here and another one chord here, and counting either differential or continuation math, you're choosing, you're counting things like this. But this means that if there exists such a solution, then this one chord and the input one chord and the output one chord should belong to the same homology class here. And because I know that each of my generators belong to different homology classes, there actually cannot, so I already told you that there cannot be any differential. There also cannot be any continuation map except the ones that match xi comma m to xi plus 1 comma n. So everything splits into this z many copies. When I'm considering only the chain complex structure, when I consider products, then they will start getting mixed up. Okay, so there's this extra grading, but of course it's a graded, with that it will be a graded module. Graded algebra. So when you take two pure pieces, then take their product, their grades will add. Okay, so now I used this notation for the kind of orbit, the one chord of the ith Hamiltonian, which winds around m times. I represent it like this, and this is an intentional choice because this generator xi to the m is nothing but xi1 multiplied with itself m times with the pair of pens product. Okay, so this is something you have to prove. It's not completely obvious, and you can say that the same thing with y's. Okay, and you can also prove that these generators actually commute. Okay, and not only do they commute. So if you look here, so x1 y lives somewhere here, and y1 y lives somewhere here, and there is some solution to there. So if you take the product of this with this, there's going to be actually something that there's a non-trivial pair of pens product where you approach in the output to this generator 1. Okay, and this one has a non-trivial topological energy. It's given by kind of the length of the interval plus some error term, because these orbits are not happening exactly at the boundary, but they're happening slightly outside of the boundary. Okay, so you don't exactly capture the area of this this shaded region here, but a slightly larger one. Okay, but as you increase I, this error is getting smaller and smaller. Okay. Okay, so now I described to you each of these C, F, H, I, comma, L's as lambda 0 algebras. They live in degree 0, and their product is given by this rule where if you multiply the x chords, you get x chords, but the winding numbers adds up. The winding numbers add up. Same with y's. And if you multiply the x generator with the y generator, you almost get 1, but you don't get 1. You get t to the almost the area of this finite cylinder that I fixed. Okay. And now I also have to analyze the continuation maps. And as I said, this winding number is going to be preserved under the continuation maps. So you only have to look at where xi1 goes. And for example, these maps, like this determines everything because of the compatibility with the product structure. And this will be so that the x generator of the ith Hamiltonian is almost going to the x generator of I plus first Hamiltonian, but there's this little error again because these generators are coming closer and closer to the boundary. Okay, but it's so that these this bound, so you know this maybe x1, maybe x31 was here, and this is the end of my. Can you see what I write? Yes. Maybe this is the end of my cylinder, so it has to kind of slowly come here. So this is this delta that these little errors are converging to. Okay. So now, if now you want to compute the limit of this diagram, and again, it's just so as a module, you only have to kind of consider Can you hear me now?
Yes, we lost you for a while, but it's okay.
Okay. Yeah. So as a Novikov ring module, it becomes this guy. So it's generated by x and y generator. So I'm now kind of allowing x to the sum, x to the positive powers and y to the positive powers. So they are all here. And there's this relation. Again, maybe let me write it like this. Okay, so now the thing that's kind of bad here is that I didn't actually get the Novikov ring. I got the maximal ideal of the Novikov ring. Okay, and this regularization that I mentioned has to do with the fact that I would like to make this actually the Novikov ring. So what I do is I take this Novikov ring module, I tensor with the Novikov field. The Novikov field admits evaluation, and now I consider all the elements which have valuation non-negative. So this has the effect of kind of pushing everything a little bit back, so that this actually becomes this. So this is this technical regularization procedure, and I also have to complete it. Okay, because that's part of my procedure. So this is what I wanted it to be. This was my claim. So it's something, it's a completion of the polynomial algebra that's generated by x and y, where if you take the product of x and y, you're going to obtain t to the length of the interval, or the symplectic area of the cylinder. Okay, so any questions about this? Okay. So now I want to slightly generalize this computation, and this time I'm not gonna explain the computation, just tell you what the result is. So now let's consider the symplectic manifold, which is kind of which is again so this is the base, and these are the fibers. So it has a Lagrangian torus fibration over Rn, and the fibers are Lagrangian tori, and it's just explicitly it's just this Rn modulo Zn cross Rn with this standard form. dpi, dqi, and these are again the p coordinates, and these are the q coordinates. Okay, so the r mod z and r's are matched. Okay, so it's a product of the previous case that I described here. It's just this case, but you take product with itself as many times as you want. Okay, now this has a Lagrangian torus fibration with base Rn. Okay. So now inside this base Rn, I consider a compact, what I will call a convex rational polytope. Okay, so this is a subset that's compact, connected, and it's given by the intersection of finitely many half spaces like this. Okay. And these half spaces are defined by kind of functions being non-negative in these regions where the functions are integral affine functions. Okay. So these are functions which in q coordinates look like this. So this is from I equals 1 to n. It has a linear part, but the linear part is so that the coefficients are integers, and it also has some affine part, some addition of a constant part, and that could be any real number. Okay, so it's something that's like this, where each of these hyperplanes have rational slope. But it can also be a degenerate one. For example, a point is also a convex rational polytope. Okay, because you can express it as, you know, this half space intersected with this half space, and this. So you can represent a point in this way as well. So I'm not assuming yet that these convex rational polytopes are non-degenerate. So of course, if n is equal to 1, the interval that I considered in my previous computation is an example of such a convex rational polytope. Okay, so now I want to consider the following functions on this polytope. So I want to consider integral affine functions, which are just functions that I just defined. Integral affine functions that are defined on the entire Euclidean space, but I would like to only consider them. So in this notation represented by this greater than or equal to 0 sign, I want to look at the ones that are not negative on this polytope. Okay, and now so I want to kind of stress that it's not important that I put Rn here, but it is important that I put some open neighborhood of this polytope. So for example, if the polytope is a point, I'm not only looking at the value, so the function is not determined by its value on the point. Okay, so so it has to extend to an open neighborhood of it, but also it should be positive on non-negative on the point. Okay, so now using this, I would like to define some kind of function, some kind of sheaf of functions. Okay, some kind of this O of P. So to each convex rational polytope, I would like to associate some kind of algebra of functions. And the way I do this is I consider this non-negative affine functions on P, and I take its group algebra with some arbitrary commutative ring K. Okay. So so that something in this group algebra is something that's a finite sum, where you have kind of formal linear combinations of these so some kind of exponentials of GI, which is just some kind of formal notation. And these are finite sums, and you take such a finite linear combinations, and the product is defined so that G times EH is EG plus H. So this is an abelian group, so I use the plus notation. Okay, so this is just the group algebra. So this is the kind of uncompleted function space that I want to consider. There's also a completed version of this function space. And here's how you complete it. So on this abelian group, on this, well, I shouldn't say abelian group, it's an abelian semi-group. There's no inverse. Okay. Sorry about that. So there is a valuation map from this non-negative affine functions on P, which you just kind of look at the minimum of your function. So you define the valuation of an affine function by, you take the function, you evaluate at every point of your polytope and take its minimum. Okay, and then you can define a completed group algebra using this valuation, where you allow infinite sums like this, as long as these elements GI have valuations going to infinity. Okay. Okay, so maybe I can skip this one. This is just some geometric interpretation of how you can kind of take three affine functions such that kind of the result is a constant, and how can you geometrically compute that constant? Okay, so let me skip that. Let me just do some examples. So let's consider R, okay, and take the convex rational polytope, which is just the interval from A to B, the one that I considered. Okay, so then you can compute this function algebra of functions as follows. So you consider the integral affine function x minus a. This is a function that's positive, that goes like this, that's non-negative along my polytope, and it's an affine function. And you can also consider the function b minus x, which has a graph that looks like this. And up to translating this, all the integral affine functions which are non-negative on this interval can be written as a combination of these two kind of optimal functions. Okay, so then the group algebra is generated up to kind of translating by these two functions which I called x and y, whose exponentials I called x and y. And here you have the fact that their product is equal to t to the b minus a. If you add these two affine functions, you get b minus a. You exponentiate everything, you get so maybe I will say this in the next. So I have this translational part. Maybe I say it now. So this one, the completed one. Okay, the not completed one is naturally an algebra over this ring. If you take the group algebra of this semi-group R non-negative integers, then of course by adding these constants to functions, you obtain an algebra structure on this function algebra of functions. Okay, so it used to be just a K algebra, but it's actually a K group algebra R bigger than or equal to 0 algebra. But now once you complete everything, you also complete this guy, and the completion of this guy is exactly the Novikov ring. Okay, so now here I'm considering that, and t, I called that like e to the 1, the constant function 1, I called t. Okay, so that's a one-dimensional example. Let's also do a two-dimensional example. Maybe I can make this a little bigger for a little bit. So we consider the triangle inside R2 with vertices at the origin 1, 0, and 0, 1. Again, I can consider this kind of optimal non-negative integral affine functions associated to each edge. So here I can consider the function x. Here I can consider the function y. And here I can consider the function 1 minus x minus y. And again, up to translation, these affine functions generate everything. So then this O of P, you can compute it to be kind of, you take this ground ring, and then you adjoin 3 variables associated to each of these edges, and now their product is equal to T. Okay. Okay, so now I introduced this because it is the answer to the generalized version of my computation. So now I want to compute the relative Lagrangian Floer theory of the Lagrangian L, which is again just given by setting all the angle coordinates to 0, all the p's to 0. Okay? This is the product, if you want, of the Lagrangian that are considered in two-dimensional situation. And I want to compute it inside the compact subset, which is the preimage of this polytope. And this is just C cross Rn. Okay, so now, again, this algebra, this Novikov ring algebra is again supported only in degree 0. And as a Novikov ring algebra, it's equal to this completed algebra of functions. Okay, so this is kind of just a slightly more kind of souped up version of what's in Paul Zeidel's speculations on pair of pens. And I will also point out that, again, you can show, in fact, that this, so remember that this guy was computed by not just by taking the limit of the diagram, you took the limit, then you completed it, and then you regularized it, and then you took homology. Here you can compute similar to the n equals 1 case, you can prove that it's just this limit is equal to the this uncompleted function ring. But again, you have to tensor with the maximal ideal. So again, you need to do this regularization there. And these isomorphisms, so these ones are all compatible with restriction maps. So you can define restriction maps on both sides, and these isomorphisms intertwine those. Okay, any questions about this? So this computation is also not very difficult. So the way you do it is kind of roughly like this. You take some polytope and you consider a function. So each of these, let me just stick to the two-dimensional case. So it's a polygon. Each of these edges define for you an integral affine function, and which is equal to 0 on the edge, and it's increasing outside. Okay, so each of these edges define for you such a function, so they all increase outside. Okay, you can take the one where the integral part, the linear part, is kind of primitive, but you can also just multiply this all of these functions with any positive integer that you want, and they will still be kind of 0 along this edge and become kind of steeper and steeper near that edge. So you want to consider those functions, and you want to consider the function 0 inside the polygon. And then you want to take the function that's the maximum of all of these functions. Okay, so this is not, of course, a smooth function. I'm drawing you kind of the corner locus, the locus of non-smoothness of these functions. And then you want to mollify this by a mollifier that's supported in a very small ball, and you can approximate in a very controlled way these this not smooth but continuous functions by kind of in a very nice way. And what you will get is you're going to get some kind of some manifolds of orbits near each edge. Okay, like this. So these orbits will, their homology class will be the homology class that's given by the function that vanishes here. Okay, so each of these edges defined for your function that generates an S1 action, and these kind of the orbits that I'm drawing here, they're going to live in the homology class of that S1 action. And then there's going to be a bunch of many other orbits that are living that are near these corners. And the homology classes of those are going to be kind of the homology classes which are lying in the positive cone of these two generators. Okay, so anything that can be represented as a positive combination of these two homology classes, there will be a generator, and also there will be iterates of that homology class, and there will be kind of chords that correspond to that as well. And again, there will be this kind of extra grading by the relative homology class. So again, different kind of so I didn't say that, but this kind of manifold of orbits you will have to perturb so that it becomes just one orbit, one chord, and this is possible to do. And then again, you have just one chord for each level. You have one chord in each homology class. And again, all of these chords live in degree 0. So again, there's no differential, and the continuation maps are just kind of what you expect. You send the generator to generator, and eventually you recover this result. The thing that's kind of difficult is to compute the product. And there are different ways. Generally, you try to recycle a computation that's already done. So the wrapped Floer homology of the cotangent fiber of a T star Tn, which is the Lagrangian that I'm considering here, this is computed. So you try to kind of recycle that computation to get the product. That's kind of the simplest way. There are other ways, but that's probably the best way at this point. Okay. So now these are kind of local computations, and
may I ask you a question? Excuse me.
Yes, of course.
And so,
yes.
if your polytope is not integral, so can you, I mean, get the answer in some way?
Yeah, I think, I mean, it's defined.
Yes. But
it will just, the answer will, I think, be a little bit more complicated, maybe. I didn't do the computation in that case.
Mm-hmm.
Yeah.
Okay.
Yeah, I expect that kind of, there's not going to be a generator associated to the edge, but kind of it will split into the two corners that are adjacent to this edge, everything. But I didn't carefully think about what the answer should be. So I think it's a good thing to think about.
Did he ask about non-integral polytopes?
I took it to mean non-rational slope polytopes.
Can you try to approximate by polytopes with rational slopes? Like that
you can try to approximate, but this kind of result is a little bit difficult. Like I don't think there's this invariant behaves very well according to such approximation. Like I don't think you can just exchange the limits or something like that. Because there's both an inverse limit and a direct limit, so it's kind of difficult. But I just didn't really think very hard about that. I don't know if it's difficult to make this computation. It's probably not very difficult. Okay. Boris, is that okay?
Yes, thanks.
Thanks.
Okay. Okay. Yes. So now I want to globalize these results. So what I do is I consider an integral affine manifold Q. An integral affine manifold just means that you have an atlas, a smooth atlas, where the transition maps belong to integral affine transformations. So G, L, and Z, semi-direct product. All right, so just linear transformations, and also translations. So this is the transition maps are supposed to belong to this this kind of diffeomorphisms. And I will make some two assumptions. One assumption is that I want this second homotopy group to be 0, and I will say a little bit about this assumption momentarily. And second assumption, which is kind of a harder assumption, and I don't exactly know when it's satisfied, except in the examples that I care about, it seems to be satisfied, is that you can always, so given an integral affine manifold, you can always canonically define a symplectic manifold with a Lagrangian torus fibration over the integral affine manifold. And you do it by first taking the cotangent bundle of Q. This, of course, has a canonical symplectic structure, but this integral affine atlas actually gives you in each cotangent and tangent spaces an integral lattice. And in the cotangent bundle, you just mod out by this full rank integral lattices. And you obtain a symplectic manifold because the symplectic structure descends to this quotient. And I will call it XQ. Okay, and XQ has a Lagrangian torus fibration to Q. It's just the map that descends from the projection of T star Q to Q. Okay, and the assumption is that I should be able to do Floer theory on this. So I assume that this is geometrically bounded. So now, if Q is closed, then this geometrically bounded, of course, is not an assumption. That's automatic. But the first one, this pi2 being the second homotopy group being 0, this actually is also not such a strange condition because there is this conjecture called Marcus conjecture. And the Marcus conjecture says that if you have an affine manifold, which is not necessarily integral, this affine manifold is complete or geodesically complete, which are equivalent to each other, if and only if there is a parallel volume element. And if something is integral affine, then this parallel volume element assumption is automatically satisfied. So what you expect is that in that case, Q is actually just, you take some flat Rn with its standard integral affine structure, and you mod out by some group G acting properly discontinuously on Rn by integral affine transformations. And this is what it means to be complete. And Marcus conjecture says that if you're closed, then if you're a closed integral affine manifold, then you have to be complete. Okay. So, and if you're complete, of course, if you're of this form, then this pi2 condition is automatically satisfied. So that's not such an unnatural assumption. And I mean, that's a very naive conjecture that I make, is that I also claim that this symplectic manifold with a Lagrangian torus fibration is geometrically bounded if and only if this Q is complete. So if Q is not closed, then completeness is not automatic. And it seems very reasonable, but I have no idea how to prove it. Okay, so but in the end, I just make these two assumptions. Okay, so now inside this integral affine manifold, again, I can consider convex rational polytopes. These convex rational polytopes, by definition, are all contained in integral affine charts. And inside an integral affine chart, then using the map, you can think of it as a subset of Rn, and it should be a convex rational polytope inside that Rn. Okay, and so that's the definition of convex rational polytope. I can again define these algebras of functions, completed and uncompleted, and it's defined exactly the same way. You look at kind of affine functions, which are non-negative on P and extend to some neighborhood of P. And the completion is again done, you just use exactly the same formulas. And in fact, if you take an integral affine chart, so phi, so there's this is the domain of the chart, and this is the subset of Rn, then you have P here, so you can move P to Rn and get this convex rational polytope phi P. inside Rn, and you immediately, just by definition, have a canonical isomorphism of this algebra of functions on P defined inside Q, and algebra of functions on the image inside Rn of P. Okay, so this is kind of automatically local. And the same with completions. And also these are compatible with restriction maps, as long as, you know, everything is contained in, you know, as long as this equation makes sense. Okay. So now inside this XQ, this symplectic manifold, I also can consider the Lagrangian, which is given by, you know, it was T star Q modulo some lattice. So inside T star Q, you have the zero section, and this zero section descends to the quotient and gives you a Lagrangian section of this Lagrangian torus fibration. Okay, and you can check that under this assumption, pi 2 of Q being 0, this relative homotopy group is equal to 0. Okay, so I can do Lagrangian Floer homology with no problem. Okay, so now here I call something an almost theorem. I thought it was a theorem, and I found a mistake in my proof, but I think it's not. It shouldn't. I don't expect it to be really that difficult, but I still have to work some things out. So it's kind of. So I computed in the local case inside Rn cross R mod Z to the n. I computed kind of the relative symplectic, relative Lagrangian Floer homology of this section, zero section, with respect to any convex rational polytope. Okay, so this one kind of is, I know O R N P, sorry, actually not P, because I have this chart, phi P completed. So this one I proved. And I know that this one is actually local. So this O, Q, P completed. These are just the same by the definition. So you would want this relative Lagrangian Floer homology of the zero section computed again in the pre-image of this polytope P to be the same, to be isomorphic to its local version. Okay, so kind of I claim that you can kind of just forget about the rest. You only, for this computation, you only need to look at a neighborhood of P. Okay, so what do you have to do to prove something like this? You first, so I explained to you how I can kind of explain to you how I can do this computation, where you would choose this kind of J-shaped data, where you have kind of orbits near the boundary and then everything goes off to infinity. Here you can't do that because the topology changes. So here you choose S-shaped data, which means you choose the same J-shaped data near P, but then you make it, you make this kind of, you make the slopes, you make the functions flat again and kind of extend almost, extend by flat function to the rest of the manifold. Okay, so you choose this kind of data, and here you kind of already have the copies of the generators that you would see in the local case, but now you also have these extra generators. Here and also outside, there are some critical points. So you have to prove that these generators die, they don't contribute. This is some general expectation that the outside generators kind of shouldn't really contribute all that much, but something that's not general is that you also want the differential and the product to be local as well. So here, you know, even if I have two generators that are local, I might still have a differential that connects them, that explores the rest of the manifold. So here you can prove that these things don't, you can't prove that they don't exist, but you can prove that they have high energy. So with this completion procedure, kind of, they don't contribute in the end. And here, kind of, the key point is this, again, kind of, there's this this winding number, which is locally defined, this homology classes of these one chords. And in fact, these, even globally, these don't come, kind of, they still are disjoint from each other. They still belong to different relative homotopy classes. Okay, so you use that and further arguments, and hopefully I'm not wrong, and this theorem I can put some. So I do want to stress that it's not trivial, the theorem. So the corollary of the theorem is that I now have a computation of this relative Lagrangian Floer homology group in this global situation. Okay, it's again given by this completed algebra of functions on P, which by definition is a local thing. Okay, and again, this is compatible with restriction maps. Okay, so what am I trying to do with this? So, so now, if you look at Q, this Q also gives rise to a rigid analytic space. And this rigid analytic space has been considered by many people, and you can, it's kind of not difficult to construct. It's something that's quite easy to construct. You use this, you look at this non-Archimedean torus, lambda star to the n, which has a valuation map to the Rn, some kind of non-Archimedean analog of the log map. And if you have an integral affine transformation of these bases, then you can lift it to an analytic automorphism of the torus upstairs, the rigid analytic torus. And then if you have an atlas, an integral affine atlas, you can just consider the pre-images of those domains of your coordinate charts into this non-Archimedean torus, and kind of glue those pre-images using the lifts of these integral affine transformations and obtain an analytic space. But it's a rigid analytic space. And kind of it's, you know, it's a more or less established thing that the symplectic homology of this XQ is mirror to, so mirror is very vague, but Mohammed has some very kind of explicit statements. So given a Lagrangian here, you can define a coherent sheaf on this, and in fact, you can extend it to a functor from the Fukaya category to the category of coherent sheaves and so on. So it's kind of established that these two are mirror. And what I want to do is to kind of upgrade this mirror symmetry statement to something a little bit more, which has a little bit more structure. And kind of this this actually follows the general kind of philosophy of mirror symmetry, where you're not supposed to have two things that are mirror to each other. You're supposed to have a family of symplectic manifolds, which is mirror to a family of complex, or in this case, rigid analytic manifolds, let's say, roughly, where there is a central point in the symplectic family, which is the large volume limit, and there's a central point in the B-side family, in the analytic family, which is kind of a maximally unipotent point. It's a large complex structure point. So that's what I want to capture. And I want to capture this by kind of, in order to do this, you have to equip your symplectic manifold with more data, which will tell you what the large volume, the associated large volume and large complex structure limit points are. And to do this, you choose a decomposition of your integral affine manifold into Delzant polytopes. So convex rational polytopes, which satisfy the additional Delzant assumption. Okay, so it looks very schematically something like this. So you have Q and you have these kind of Delzant polytopes that are covering it. So now, given such a decomposition, I'm going to be very kind of vague at this point. You can define a symplectic submanifold of your of XQ. It's kind of it's going to be something that's associated to a dual graph to the decomposition. So in the two-dimensional case, it's like for each polytope, for each Delzant polytope, you have a point, and each edge that's adjacent to two polytopes is connected by an edge like this, and so on. So this is something that roughly is like a tropical thing, but it's not really a tropical thing. It's a much softer object. What you can do is you can build a symplectic submanifold that lives over this. Okay, so near each of these edges, so this, as I told you, that this edge defines for you an S1 action, a local S1 action, and you just kind of, so that defines for you kind of a cycle upstairs, and you choose your symplectic submanifold such that here it carries exactly that cycle. And if you look here and look at that cycle, you get a Lagrangian. If you look here and look at the same cycle, you get a symplectic manifold. And there is some kind of, there's Mihalkin's work, or there is also some new work by Vienna and Casals, where you can also kind of glue these things together. The only requirement that you need is there is some kind of balancing condition, which I'm not really spelling out. And somehow you can construct the symplectic submanifold such that it's disjoint from the Lagrangian, the zero section Lagrangian that I constructed. And in fact, it's a kind of, even after you take S1 actions, these local S1 actions near edges, it's disjoint from the symplectic manifold. Okay, so this symplectic submanifold is kind of, it's what lets you define the large volume limit of the symplectic manifold. If you remove this, this symplectic submanifold, which depends on P, on this subdivision into polytopes, you get an exact symplectic manifold, and that's going to be kind of the large volume limit. And on the other side, given such a decomposition, you can define what's called a Reynaud model of the rigid analytic space that I said, for example, was considered by Abu Zaid. And you can do this in such a way that the special fiber of each special fiber of this Reynaud model, which roughly kind of lives, so there is some special fiber, and this special fiber just corresponds to kind of setting t equals to 0. And that should be mirrored to this large volume limit. Okay, so I mean, of course, this is, if you don't already know what this is, it's impossible to understand, but the Reynaud model is a formal scheme over the Novikov ring whose Reynaud generic fiber is the given rigid analytic space. So it's some kind of finer thing. And you can recover if you take the generic fiber, you recover the rigid analytic space. If you take the special fiber, you get some kind of singular space over the base field K. Okay, and if you subdivide your decomposition, that corresponds to kind of blowing up the special fiber. If instead of Delzant, you assume actually each of your polytopes are simplices, then you get normal crossings, special fiber, and so on. And the construction is by kind of so I told you that I defined for you these completed algebra functions, and there's this thing called the SPIF. It's kind of something like spec. So it's some geometric object associated to a topologically finitely presented algebra like this, and you can glue these things along the things that are associated to the edges. Okay, so maybe instead of saying why that works, let me just show you a quick example. So here I have a picture of the base of R mod Z cross R mod 2Z, R mod Z squared cross R mod 2Z squared. So this is the base and this is the fiber. Okay, and now, so my base is just this R mod 2Z squared, which I represented as the square, but the two sides are identified. So now you can take a decomposition of this base into some polytopes, polygons. And these are Delzant polytopes. In fact, they are simplices. And each of these triangles, each of these Delzant triangles, I know kind of what I'm considering. I'm considering this completed algebra, this topologically finitely presented algebra. And you can also see that because there's some integrality here, it's actually, you can define, instead of the Novikov ring, you can define something over the formal power series ring in one variable. And so each of these guys, you have this this ring, and you can, so whenever you have two of them intersecting along an edge, there is a so each of these edges also have their own algebras, and if you consider the duals of restriction maps, they're open subsets of the polytopes, that they're the spaces that are associated to the polytopes, and it allows you to do gluing. So there's the co-cycle condition is satisfied, and so on. So I wanted to say a little bit more about that, but I'm over time, so maybe I'll just stop here. I think I'm over time, right?
It's fine. Thank you very much. Okay, so are there any questions for Umut?
Can you make a kind of conclusion of the last part of the talk? So kind of you are gluing things from these pieces, and so what is the kind of conclusion?
Yeah, so okay, so good question. So good question that I don't have a very good answer to. So something that I think this should help with is there's kind of a an unexpected extension to the story, which is the following. So now I have this kind of symplectic divisor, infinity, and this has its own symplectic topology. So it has its own invariance and so on. So there is a conjecture by Aru and also Lekili and Ueda, which tells you that somehow this symplectic topology can be recovered from the symplectic topology of its complement. And what they suggest is that you should consider the wrapped Fukaya category of the complement and take its quotient by the closed Fukaya category. And this means something kind of very clear in the mirror, where kind of you have this kind of singular space, which is supposed to be mirrored to the complement. And by that, you mean the following. So there's the wrapped cohomology, wrapped Fukaya category, which is supposed to be mirrored to kind of the category of coherent sheaves, all coherent sheaves. And there's also this closed Fukaya category, which is supposed to be mirrored to the category of perfect sheaves, perfect modules. Well, in the affine case, they're perfect modules. In this case, they're just perf of this singular variety. And it's known that this quotient, this modding out the coherent sheaves by this perfect ones, it gives you what's called the singularity category. And the singularity category was, so I talked about this paper of Paul. And kind of one of the main conjectures in this paper of Paul was that kind of the Fukaya category of this symplectic submanifold is given by this singularity category. So he didn't consider, as far as I know, he only considered the abstract, he didn't consider the thing that this symplectic manifold was embedded in. He only considered the symplectic manifold, and he said, okay, its symplectic topology should correspond to the singular category of this, what I constructed as the special fiber of this Reynaud model. And I think that there is a strategy to prove all this by a local to global way. So each of these triangles, each of these triangles, kind of, there's some local model, and maybe this kind of capturing the topology of the divisor from the complement thing is actually already proven for each of these local models. And then there's kind of a local to global principles like the one that I had in my thesis. And I think it should be possible to kind of glue together these local statements to a global statement such that you prove this conjecture of Aru and Lekili Ueda. This is one thing that I think can come out of this.
Thank you very much.
So there are two questions in the chat. I don't know. I could read them if you want. There's a question by
in the local computation. is the relative invariant related to the quantum homology of the symplectic manifold of the polytope? Not in a very obvious way. So there's another piece of data. So if you have some symplectic manifold like this one here, where you have a decomposition into polytopes of the base, this gives rise to some kind of degeneration of the symplectic manifold to some kind of union of toric manifolds, like the one that you're mentioning. It's some kind of inverse of the, well, I don't know which one's inverse, the symplectic sum construction. There's this kind of multifold symplectic sum construction, where if you have some kind of normal crossing singular variety, if some condition is satisfied, you can kind of smooth it and get a smooth symplectic manifold. But this degeneration is not a very good degeneration in this case. I don't think it's useful for much. It's the total space is not going to be smooth. It's not going to be, so I don't know. It's a kind of something. If you had a decomposition that was more like this, a trivalent decomposition like this, which appears kind of as the dual in this picture, then the degeneration that this gives rise to is a nice degeneration. It's what Tehrani, Zinger, MacLean call a multifold cut construction, a multifold cut configuration, something like that. But it appears as the dual here, and the one that I consider this, the decomposition that I'm using here, doesn't give rise to a good degeneration. This is my own answer. I don't. Johan, is this okay or?
I mean, just for the local case, if you don't do the degeneration, say if you have a triangle, you calculate the relative invariant of the section. Is it related to the quantum cohomology of CP2?
I don't have a very clear, I don't have a good answer. It's probably related, but I don't know what to say. Okay.
Yes, thank you. Yeah.
Chris Woodward says, so maybe it's just, I just don't know probably. And I have to talk to, Chris about this, I think. It sounds like, so you're seeing the answer, right?
Yes, thank you. Yeah.
I actually don't know this.
There's another question by
yeah. Well, so it's not exactly that. It's a completion of that, right? It's you know, it's if you don't do any of this, look, if you just compute the wrapped Floer homology, then that's what's isomorphic to the homology of the base loop space. But here we're also kind of taking a completion with respect to some compact subset, which in the cases I don't know, you wrote T star Tn, but if it was T star Tn, then you could consider these pre-images of polytopes, and it will be some completion. Like I wrote down the answer in this case. It is so in the case of torus, the homology of base loop space is just the Laurent polynomial ring. And the answers that I wrote down are some completions of the Laurent polynomial ring. Okay.
Okay. I don't know, any more questions?
I have a question. So when you talk about decomposition on the base, you mentioned some balancing condition. Can you explain a little bit?
The decomposition doesn't have any. It's just into Delzant pieces. But this symplectic, this dual graph that I'm considering. So in this case, if I decompose things into just this kind of minimal simplices, like integral simplices of minimal volume with vertices on the lattice points, and then this condition will automatically be satisfied because the homology class coming from this edge, and this edge will add up to 0. But in more complicated cases, you have to you might have to take multiples of this class to be able to really get a surface. As the balancing condition is so that you can lift this graph to a symplectic submanifold. It's not really a balancing condition in the sense of a tropical manifold. It's a weaker thing than that. It's like each of these edges carry a cycle, and this you can also it doesn't have to carry exactly that cycle. It can carry kind of any positive multiple of that cycle. And if you want to be able to do this matching, things coming from these three edges, you need some condition to be satisfied, because those homology classes need to add up to 0.
Okay.
Sometimes
yes,
it's
okay.
automatic.
Okay. Thank you.
Yeah.
Okay. Maybe that's it for the questions, or we can thank Umut again.